Welcome back to the channel. I'm Daniel with CMC Learning, and today we're going to have a quick look at modulus functions, and more specifically, how we end up graphing them. So let's get straight into it. What do we know about the modulus function? Well, we can write it as these sort of two parallel bars around a number, and essentially the modulus function, as it sort of sounds, is a function. If we input a positive number into this modulus function, we get back a positive number. If, however, we input a negative number, we get the positive value of that number. So if I were to put in -5, all I would get is just 5. And this works for any number, so this can work for decimals as well. You can put in, for example, -pi, and you would just get returned pi. So more interesting things happen when we actually plot this on a graph. So if we have a look at some relationship, y is equal to the modulus of x, so that's the terminology for that. Let's see what sort of graphs we would get from this. First, it would probably be worthwhile to actually plot just y is equal to x in general. And I'm sure this is a plot we all know. A straight line with a gradient of 1, essentially. And this goes from all values of -x to all values of +x. So let's redraw some x's, and let's have a look at what happens to each of these points as we plot them. Let's maybe first have a look at these positive values of x, because as far as we know, the modulus function does nothing to these positive values. It leaves them completely unchanged. So I know I'm going to have a set of points like so. So essentially just mapping x to y. For x is equal to 0, the modulus of 0 is just 0. It's another interesting property. But now let's have a look at some of these negative values. So if I wanted to plot -1 on the x-axis, I know my coordinate would be here, but the modulus function is just going to turn a negative value into its sort of positive value. So instead of -1, we're going to end up getting +1, and so on and so forth. So we can do the same for all of these negative values of x, as far as we need to plot. And hopefully we can see some sort of pattern arising. If anything, we have some sort of reflection about this one point where the inside of our modulus function changes from positive to negative. If we were to plot this with a definitive line, it would look something like this. Obviously, continued it up quite nicely. There's an interesting property about what we do to each of these points when they are negative. So if we have a look, essentially what we can do is multiply these negative values. If we're bringing them up, we're reflecting them in the x-axis. It's very similar to multiplying by -1. I'm sure if you remember some of your stuff with functions, if we multiply something by -1, essentially a y-coordinate, we flip it up in that sort of x-axis. So all of these values are multiplied by -1. Okay, so that's an interesting property. We can see that when the inside of our modulus function is negative, that's the equivalent of multiplying by -1. Now the aim is to be able to write some more drastic functions of sort of y is equal to modulus and then some function of x. To be able to write some more drastic functions, see if we can write them as just two separate lines. So I'm sure you can see here, this line for positive values of x, we can just say is y is equal to x, can't we? Things are slightly different for the modded negative values. Essentially this line here that's going -5, 5, -4, 4. This looks similar to a line with a negative x gradient. So this we could say is -x. what we can do is reinforce that idea by having a look at y is equal to the mod of x minus 5, for example. So what do we think is going to happen here? If we look at our function, we can plot the general expression for, let's say, positive values of x. If we were to go through them bit by bit, we can see that when x is equal to 0, we get negative 5. So we can plot that somewhere here. When x is equal to when x is equal to 1, we get negative 4. You can see that this will just go on and on. So negative 3, negative 2, negative 1. And when x is equal to 5, we just get 0. And if we were to keep plotting, we would just end up with a straight line. This is y is equal to x minus 5. We now need to pay attention to this modulus. So remember, we're multiplying essentially all of these negative y values by 1. So that's flipping all of these up into essentially the positive y value. If we were to plot a line through here, this is what we would get. The interesting point here, just to reinforce that idea of, if you will, this turning point, we can see that when x is equal to 5, our function flips. And that is coincidentally when the inside of this modulus function is equal to 0. So that's quite an interesting property. Essentially, we can write something quite interesting about this function here. We'll rewrite it off to the left. Essentially, what we're doing is we're writing this as two different functions, just with two different sort of conditions on the values of x. So we can say that at some point, I'm going to have just the regular x minus 5 plot, and this just so happens when x is greater than 5. And on the complete other side, we can see that we're multiplying all of these values below 5 by minus 1. That's the same as multiplying essentially the inside of this function by minus 1. We can have a look at what we would get by that. Essentially, we're doing minus 1 multiplied by x minus 5. This gives us minus x plus 5. If we have a look at this portion of the line, that is exactly what we get. So a negative gradient and a y-intercept of 5. So we can say that that is the second line that is plotted here, minus x plus 5. And then we need to give a condition on these x values. This happens when x is less than 5. So we can see we can split this up into two distinct lines, and this might help for things like finding intercepts. If I wanted to find this intercept here, or this intercept here, I need to know which line I should be using, which equation of the line I should be using. So that is one application of these modulus functions. Let's now have a look at seeing if we can plot some general expression, some general modulus function. So let's write something completely general. We're also going to mix it up here. We're going to put a prefactor behind this modulus function, and we're going to see what it does. So I'm going to put here a factor of minus 2. Something like this. We could even put a plus 3 on the outside, just to see how something like this would work. If you're at all familiar with manipulating functions, you should understand that this is very similar to transformations on some f of x, where we either multiply by minus 2, plus 3. In some way, this is sort of the inside of our function, and these would be things that we manipulate on the outside. So we're multiplying the function by minus 2, we're adding 3 to the function. Those would be those sort of final steps. As that happens, or as that is, we should probably work with this modulus function to begin with, and then start adding on these external bits. Okay, so let's have a look. We can think of some definitive steps here. I think the first step here is to find out where this turning point is, if you will. If we look at all of our functions that we've applied so far, we can see that there is some point where our graph switches from essentially one gradient to another. We call that a turning point. As we said previously, that happens when the inside of our modulus function is equal to 0. So let's have a look here. Essentially what we need to show is, or what we need to find, is the point when the value of x when this is equal to 0. This we can find quite nicely as equal to 2 over 3. Okay, we treat this as our turning point, which is quite nice. Now what we should aim to do, is write this function here as two sort of separate functions. I can do that with these sort of curly little brackets here. I want to write two separate functions with two separate conditions on x, and essentially when I put them together, when I consider them both, I should get my modulus function. So the easiest one to do is to just start off with when the inside of our function is positive. And all we have to do there, as we've shown in the previous examples here, we can just leave this function alone. So y is equal to modulus x is just equal to y is equal to x when x is positive. So let's have a look. Essentially, we're doing nothing to this function, and we need to see what values of x we should use for that. So we need to consider, essentially, when this function here is greater than 0. As we can see that just by using this condition up here, we can also write an inequality. So 3x minus 2 greater than 0. When we solve this, we get x is greater than 2 over 3. So that can be our condition for our values of x. Okay. Very similarly, as we've done before, when the inside of the modulus function is negative, we need to multiply it by minus 1. So what I'm doing is doing minus 1 multiplied by 3x minus 2. In return, I get minus 3x plus 2. And that's what I can say is my line, or the equation of my line, sorry, for negative values of this modulus. Now we can do the very same thing. Let's consider when this is positive. We should get something essentially the opposite of this. Let's have a look. We need to find a value for x such that minus 3x plus 2 is greater than 0. We can move the 3x to the other side, divide by 3, and what we're left with is 2 over 3 is greater than x. In other words, x is less than 2 over 3. And if we're considering all values of x, so all negative and positive values of x, this should cover our basis quite nicely. Of course, we're sort of ignoring the idea of equal to, but that ends up just being a coordinate on its own. If anything, these could be sort of equal to values. So let's have a look here. We've essentially plotted, we've separated our modulus functions to two separate lines. We can actually plot this just to see what we get. We can try and do it somewhat accurately. First thing we should do is write down what this turning point is. So essentially we can see our turning point is 2/3. If I were to stretch these axes, I could put that somewhere here, for example. So 2/3, that would be our turning point. When x is greater than this value, what I want to do is plot just a regular 3x minus 2 line. So obviously that 3x minus 2 implies we have a negative y-intercept. But we need to remember that the sort of minimum point we're plotting here is 2/3. So if I did give 3x minus 2 the point of 2/3, should get 0. So anything greater than 2/3 should give me something positive. So for example, 4/3. If we have a look at what that gives us, we should get some nice straight line from that, essentially ignoring lesser x values. Then we can also have a look at the other situation. So when x is less than 2/3, we want to be plotting something like this. So let's have a look at what that gives us. A negative gradient of -3 and an intercept of +2. That looks something like this. It's somewhat important to make sure that these sort of look mirrored in a way. It's not too important as long as you sort of get the coordinates right. Of course, this diagram here is not to scale. We can obviously add our axes, just not to forget. So to add some stuff here, we have a turning point of x is equal to 2/3. If we were to write that as a coordinate, 2/3 and 0. And we have a y-intercept for our negative values. This would be at 0, 2. That'll be this point there. Okay, and that would be our modulus function. Essentially, we just need to choose, depending on which part of the graph we want to look at. If we want to look at values greater than 2/3, we should be using this. Values less than 2/3, we should be using this. So that's something to keep in mind when doing, for example, intercepts. Here I might want to look at values are greater than 2/3. But keep in mind we haven't yet plotted the total function here. We still have some translations to do. So the order of which we should do these is first look at how we scale this function. In this case, we're scaling it by a factor of -2. I deliberately chose a negative value here to show that essentially the modulus function, just because you see the modulus function in any expression, doesn't necessarily mean you can't have any sort of negative values of y. It would be good to sort of show at each step what we are plotting. In this case, we're plotting 3x minus 2. So let's have a look at the next scenario. Here, I'm going to plot this -2 factor behind it. So y is equal to -2 multiplied by the modulus of 3x minus 2. Okay, so anyone familiar with their function translations should understand that what we could say we're doing is scaling in the y by a factor of 2, essentially multiplying every y coordinate by 2. But on top of that, we need to multiply by -1. If we remember from the very beginning, the act of multiplying by -1 can go both ways. So, if we have a negative value of y and I multiply by -1, that makes it a positive value. If I were to do the opposite, for example, if I wanted to translate this y is equal to x and flip it in the x is equal to 0 axes, I could just multiply all of these points by -1 and get the very same thing, essentially change the sign of my y coordinate. So it would be good to sort of do both in one step. I guess it is, in this case, somewhat trivial. We can just multiply the y coordinates by -2 and see what we get. So we should really be looking at the sort of key characteristics of each of these plots. You can see that this sort of turning point, since the y coordinate is 0, nothing really happens to this y coordinate. This y coordinate remains 2/3 0. But this y-intercept for the negative sort of values of our modulus are quite interesting. Here this 2 goes to a -4. And we could obviously, or what we have to do, obviously, is do this for every single point on our graph. So what we end up with is essentially a narrower line, or essentially our reflection is a lot narrower than above. Hopefully that's somewhat clear. We can now plot our new point, 0, -4. Okay, good. And the last thing we should do is consider that final translation. So in this case, we need to add 3 to the end of our function. It's always good to do this as a last step. It just makes it a lot clearer, in my opinion. So let's see. All we need to do now from this previous step is add 3 to the y coordinate of every point. So again, those familiar with functions, we're just shifting this vertically by 3 units. If we were to plot each of these points, we can see that 0 minus 4 would now become 0 minus 1. So we can plot that point here. And on top of that, our 2 over 3 as our x and our 0 as a y now becomes 2/3 as the x and 3 as the y. That should look something like this, obviously not completely to scale. And what we should notice, is we end up with some more interesting points to consider here. Here we can see we have 2 new x coordinates. And as a little exercise for you, you could use Desmos to sort of verify your work. See if it's possible to find out what these x roots are. Essentially, the value of this function when y is equal to 0. And this should give you the value of those roots. And like I was saying, use Desmos or some sort of plotting calculator, graphing calculator, to see if you get the correct answer. So quick recap, we might as well put all the coordinates of these points as well. So raised by 3, this be 0 minus 1. So quick recap on modulus functions. We completely flip the sign of whatever we're working with, only from negative to positive. Looking at functions, we're going to have some characteristic turning point, depending on when the inside of this modulus is equal to 0. And then we need to consider essentially these boundaries, if you will. One where the inside of the modulus is positive and negative. You then split the function into those 2 lines, and then do necessary transformations afterwards. So scaling factors on the modulus function, like this -2, or translational factors, like this +3. Okay, so I hope that helped. Hopefully good little introduction or revision on modulus functions. If you have any questions, do be sure to leave them down in the comments below, and we'll see you in the next video.